the next typical sort of ones, as you see, because I think every extension 2 paper we've given you so far, there's been an induction question in there. Now, inequalities, it can be in 3 in it, of course, but I thought we'd just look at the inequality one first. So, yes, first case, let's test n equals 1. Left-hand side, yes, equals 1. Right-hand side, oh, it equals 1 as well. So, yes, indeed, the left-hand side is less than or equal to the right-hand side. In this case, it happens to be equal to. No, you cannot set yours out this way. I'm just doing this to save a bit of time. Okay, so our assumption would be for n equals k. We're going to prove n equals k plus 1. Now, it is a series type, so I'll do it the same way we always do series types. Let's write out all the terms, making sure I've got the second last one in to make it obvious where my assumption is going to go. But in this case, instead of being equal to, it was less than or equal to. And we're trying to show this is less than or equal to 2 minus, what was it, 1 over k plus 1. All right, well, I've got the 2, so I'm not going to do anything with that. It's the minus part we want. So let's combine that all into one fraction. Now, ideally, I want 1 on k plus 1. Bottom of the fraction, my common denominator there is k plus 1 squared. So it would be nice if the top ended up being k plus 1, then it would cancel. So, all right, let's expand that out. I've got k squared plus k plus 1. Well, k plus 1 is k squared plus k, so it's close. But of course, we're dealing with inequalities here. I could, if I want to, split that up into 2 fractions. K squared plus k, that's what I want. But then I'd have this other one, minus 1 on k plus 1 squared. So in fact, that line there must be less than what I actually want. Because I would like to have just the k squared plus k on k plus 1 squared, k plus 1 squared. But I've got this additional bit. So, because I'm dealing with inequalities, I can say, well, yeah, that line is less than 2 minus k plus 1 on k plus 1 squared. K plus 1's cancel, and we've got the result we're looking for. So yes, therefore, that is less than or equal to. So we've seen those sort of ones in extension 1. Now, extension 2, where is it a little bit different? In that sometimes they like to play with recursive sequences. And so it's a bit like, you know how in integration we had reduction formulas? Don't panic, you're not going to see integration and all that in there. But it's like that, where we create a formula based on previous terms. And so what we've got in this one is, they've told us the first term is going to be the square root of 2. So instead of writing out a general term, they're basically saying, we create it using previous terms. Now, I could do that with an arithmetic sequence if you think about it. Because I could say the first term is a, and then any term after that, that's wrong, isn't it? D plus term k minus 1. You're just adding the difference on each time. And so that's what this one's really saying is, well, to get the next term, I'm just going to go the square root of 2 plus the term before it. And that's how it's going to create all the terms. Now, we've got to show that it doesn't matter which term we pick, it's always going to be less than 2. Okay. Still do it the same way. Well, test it for the first case. The first term is the square root of 2, and the square root of 2 is, of course, less than 2. My assumption is going to be that term k is less than 2. I want to prove term k plus 1 is less than 2. Term k plus 1, I go and use the formula they gave me. You do not have to. This is not what you're trying to prove. A lot of people make the mistake of thinking that's what they've got to prove. That's a fact. They're telling you this is how you create each term. So I can use that. Term k plus 1 is the square root of 2 plus ak. I'll sub in my assumption. Our assumption was that term k was less than 2. So therefore the square root of 2 plus term k must be less than the square root of 2 plus 2. Oh, that's the square root of 4, which is 2. And so there you go. So often they drop out very nicely. I mean, they look complicated, but they drop out quite nice. So yes, indeed, every single term is less than 2. Now, this is a fun one, because it's got 2 sequences happening. Now, but they combine with each other. The first term of the x sequence is 5. The first term of the y sequence is 2. And to get each term in the x sequence, we add the term before it in both the x and the y sequence, divided by 2, so like the average. And to get the next term in the y sequence, we multiply them together, but then divide by addition. We've got to prove that if we grab two terms, they'll always multiply together to give 10. Okay, well, let's try it for 1. Term 1 in the x times term 1 in the y, 5 times 2 is 10. Okay. We're going to assume what we're trying to prove. xk, yk is 10. We're going to prove xk plus 1, yk plus 1 is also 10. So let's sub in our formula they told us we could use. xk plus 1 was xk plus yk on 2. Yk plus 1, 2xk, yk on xk. Well, again, remarkably easy. Xk plus yk cancels, 2's cancel, and I get xk, yk, and we've assumed that's 10, so we've got the answer. Okay. Well, couldn't do it without a Fibonacci. Fibonacci, the classic sequence of Fibonacci. We know the first two terms in Fibonacci goes, 1, 1, and then to create every term after that, we add the two previous. So it goes 1, 1, 2, 3, 5, and so on and so on. Every single term, and this is the significance of it if you recognise the number, every single term is always going to be less than 1 plus the square root of 5 on 2 to the power of n. And of course, 1 plus the square root of 5 on 2 is? That's the golden ratio. Yes. So that's the significance of that. So you can pick any term in Fibonacci's sequence and it will always be less than that golden ratio to the power of whichever term it is you picked. Okay, now, this is where it's different. Because if you look at the formula I'm going to use, it relies on substituting in two previous terms. So therefore, I'm going to have to assume two terms are correct, which means back here at test n, I'm going to have to test the first two terms. Well, in this case, it doesn't matter because they're both equal to 1 anyway. But let's have a look. Left-hand side, A1 is 1. Clever, hey? Now, the golden ratio is, of course, well, 1.62 is approximation. As we all know, a better approximation is 1.6180339. Yeah. Let's now test the second term. It's 1 as well, and then we're going to raise it to a bigger power. So, I mean, of course it's going to work, but let's just check. Squared becomes, oh, look at that, 2.62. So that one works. Okay, so I'm going to make two assumptions. I'm going to assume term k minus 1 is less than the golden ratio to the power of k minus 1. Term k less than the golden ratio to the power of k. And then we're going to prove term k plus 1 is less than the golden ratio to the power of k plus 1. All right, well, let's use the formula. They've told me we create each term that way. Now, we've said term k is less than that one and term k minus. So added together, they must be less than 1 plus root 5 on 2 to the power of k plus 1 plus root 5 on 2 to the power of k minus 1. We want to get 1 plus root 5 on 2 to the power of k plus 1. Okay. Well, let's factorise out what it is. That's an easier way of doing it. So I'm going to factorise out what I want to be left with. That leaves me, I mean, it's an unusual factorisation because normally we pull out the smallest power, but I've actually taken out a bigger power. So I'm left with negative indices inside the factorisation. So 1 plus root 5 on 2 to the power of negative 1 plus 1 plus root 5 on 2 to the power of negative 2. Now, as long as that expression is either, and you're going to tell me in a second which one, is either less than or equal to 1 or greater than or equal to 1. Which one do I want? Good morning. Okay. Yes, you've been here all night. It is your worst nightmare. No. Okay. Well, we want to show that this line is less than 1 plus root 5 on 2 to the power of k plus 1. So if it's less than, it would be a multiple less than or equal to 1?
Yes.
Because if it was 3/4 of it, it would be less than 1 time. All right, let's work it out. Let's see what we get. 2 on 1 plus root 5 is the first one. 4 on 1 plus root 5 squared is the second one. Look what happens. Common denominator, 1 plus root 5 squared. The top is 2 plus 2 root 5 plus 4, which is, of course, 6 plus 2 root 5. Those observant amongst you will realise 1 plus root 5 squared is equal to...
6 plus 2 root 5.
Very good. So actually, my question to you about less than or greater than didn't matter because it's actually equal to 1. So it's actually equal to it. So indeed, term k plus 1, if we read down, is less than 1 plus root 5 on 2 to the power of k plus 1. Ta-da! So we've got Teddy and Patel has some induction questions. I think I put a sheet in there of induction questions as well. There's all sorts. And of course, past papers and